Hey, what's up, guys? Okay, so previously we just showed some property of Euler function, right? So in order to do more, we are going to introduce basically the primitive roots theory. Okay, and this theory is very difficult to prove. It's not so difficult, but it requires a lot of work. Okay, in order to do this, I will separate like 5 to 7 videos and do it step by step. And so in this video, I will first introduce the primitive roots and tell you why this is important. Basically, the idea is that we are going to study the structure of the multiplicative group of Z mod MZ. So let me just use ZM just for the simplicity. We need to study the multiplicative group of this. And in order to do this, we need to define the definition of primitive roots. Okay, so let me just write down. So primitive roots. So in order to define it, we need to I assume that you know the Euler theorem, right? So for all the A divide it's very this is trivial, right? Because this group, right, has order 5n. So each element inside this must satisfy A to the 5m equals to identity, right? But basically mod m. Okay, so this is Euler theorem. This is exactly this for the Fermat's theorem. Sorry, the Fermat theorem. Okay. Okay, so what primitive roots? Basically, when I say x, let's say x is a primitive roots of the m multiplication, meaning that the x go to the highest power is 1. So basically, go to the highest power is 5m, which is mod m is 1. So from here that I can define an idea called order of the band notation. I remember it's order mx. Okay, so this is defined to be the let's say y is greater or equal to 1, such that x to the y is 1 mod m, and I take the minimum of y. Okay, so basically this is the people say it's called order. So order of x over n basically is all the smallest, basically smallest order, such as x to the y, which is 1 mod n. And if order of mx is 5m, we call the x is a primitive roots. Okay, and so obviously that order y, right? So any order of m of x must must be the factor of 5m, but it's not sure that whether equal or not. Okay, let's say it's doing some stupid example. So for example, m equals to 4. That what is this, right? This is basically 1 and 3. And the phi of 4 is 2. Okay. So 3 is not 1 mod 4, right? But 3 square is 1 mod 4. Okay, so 3 is a primitive roots. Okay. Let's say m equals to 5. So z phi this is 1, 2, 3, 4. And phi of 5 is 4. Okay. Let's say 2, right? So 2 is not 1 mod 5, right? But 2 squared is 4, which is minus 1 mod 5, still not 1 mod 5. But 2 to the cube, which is 8, which is 3 mod 5. And the 2 to the 4th, which is 16, which is definitely 1 mod 5. Okay, so 2 is the primitive roots here. So 2 is the primitive roots. Uh, okay. So so the fact which is notice that the primitive roots does not exist. Or also I should say not necessarily exist for all n. For example, let's say m is 4 m is 8, that this group, right, has all the number which is co-prime to 8. You have 1, 3, 5, 7, and the 5 8 is basically 4, right? Check it by yourself. But 3 square is 1 mod 8, 5 square is 1 mod 8, 7 square is 1 mod 8. So there's no number that to the fourth. So there's no number x to the fourth 1 mod 8. Right. So there's no number x to the fourth, but not x squared 1 mod 8. So this means that there's no primitive roots in Z8. Okay, and obviously that hopefully this obviously to you that if the cross has primitive roots, primitive roots, it's not important that let's say a then a to the 5m is 1, and it's obviously that a will generate this group because each element there's only 5m element, right? So that means that the multiplicative group is cyclic. It's a cyclic group. Okay, so the theorem, which is very difficult, probably requires some time to prove, is the primitive theorem, which say that if this guy is cyclic, basically, or you can say that the primitive groups exist. If only if m is 2, 4. But this is trivial, right? 2 and 4 trivial that we just showed. Otherwise, it's p to the k, where p is odd, or 2p to the k, which is p is odd. Okay. This is called a primitive roots theorem. PowerPoint. Okay. And if I notice from history that this primitive roots theorem is proved by Gauss. Okay, and in order to prove this, and I think these two are trivial. So the next video that I will try to first prove k equals to 1. Actually, there are two kind of proof to prove k equals to 1. It's actually very difficult. It's not so trivial. And to prove more, that we need a little bit amount of work. And you can use algebra or some basically, if you know simple group theory, that you can prove some of the case. But more general, that you need some other kind of tool. Basically, next video that we will develop some natural tool to solve this kind of problem. Okay, so see you guys next videos.